you to do so. If you want other personal accounts, I'll put you in touch with other people, but it's well worth going. Not to mention it's in Albuquerque, New Mexico. There's some interesting museums there. I heard that they somehow invented an atom bomb there. Okay, nobody's laughing at that one. And there's some Santa Fe up to the north there, so it's a great vacation spot. It's a great place to get your chakras aligned, and we all know in ham radio, being aligned, getting in alignment is very important. Okay, nobody's laughing at that either, so okay. So since nobody's laughing at my jokes, and I know they're bad, I'd like to let you know that TAPR is at these booths, 5001, 5003, which really is in the Hertz building. Say again? Yeah, 5001. Interesting. So two buildings over in the Hertz building. So just remember, it doesn't hurt to be a TAPR member. Oh, geez. Okay. All right. Come on by, renew your memberships, have a talk, take a look at some of the projects and everything that are being taken care of there. So that's all I have. Any real quick questions? All right, then I'm going to turn it back over to Scotty. Thank you.
Twin, he did the whole thing. Okay, next up we have Steve Ford, the editor of QST, who's going to cajole you to publish all of your secrets in QST and QEX and write for them. So, here.
All right, cajole. I'm done, Scott. No. I wanted to thank Scotty, and Steve for inviting me to speak here. ARRL has been involved with TAPR for a long time, longer than I have been there, to be sure. And it's been a symbiotic relationship, and a lot has come out of that. The reason that I am here today at HamFest is kind of as a roving news person, but also, frankly, I am on the hunt for authors, as I always am. And we are always in need of authors, especially now because once upon a time there was just QEX and QST, but now we've branched out. We have various social media channels. We even have a couple of podcasts going on now. So we have an increasing need for, as we call it in the publishing world, content. I don't care for that word myself, but we do need it. And for QST, that can be virtually anything. That audience tends to be somewhat, in general, average, somewhat less technical than most people in this room. They tend to be more what I would call system-oriented, block diagram-oriented, if you will. QEX, though, is at a much higher level. That magazine's edited by Kai Siwiak, KE4PT, I think. I always get his call sign wrong. And Kai, in particular, is always looking for good articles for that. We will consider virtually anything that seems halfway sane. The way it works is that we have an anonymous peer review committee of about, give or take, 50 engineers who are scattered throughout the world, and when an article comes in for either QEX or QST, we post it to this secret website where they access it, and they give their votes and they share their opinions and so on, and then in the end, once a month or once every month and a half, the verdict is rendered and we see who's published and who's not. But we do accept a lot of material. In addition, believe it or not, one thing that has been increasingly difficult for us to find are books and book authors. For whatever reason, and I could probably talk on for a half an hour on that, and if you're not into publishing, you wouldn't care. But book authors are becoming an increasingly rare breed. So if you think you have a technical book, the great American novel somewhere in your heart, we would like to talk to you. By all means, you can drop me a line. If you have trouble remembering my call sign, simply send it to qst@arrl.org, and that'll get to me. And if we have a book author guide that I can send you. We also have a QST and QEX author guide that I can send you for that as well. But we're not strict. We're not needy at the same time, but we're not overly strict. We give everybody a fair hearing with the star chamber of anonymous engineers. So we would definitely be happy to hear from you. Thank you, Scotty. And Scotty, you promised me a book at one time. I still don't have it.
Webster's Dictionary, would that work? Well, it's got lots of words.
Yeah, well.
We have Stana, who is going to talk to us about writing for PSR.
I used to write for QST. I have been doing PSR for 10 years. I'm not, Scott, how do I change the slides? Sorry. That's okay, forget it. That's okay.
Go ahead.
PSR is a newsletter put out by TAPR. It originated back in the 80s when TAPR was developing the TNC1, and they published it. It looked like a newsletter. Okay. And that's the first issue back in July '82. Looks like a newsletter. In July '87, it looks like a newsletter. And right up till about '84, it still looked like a newsletter, and I had taken over editorship at that point. And then I came up with this grand idea. Your computer screen is laid out horizontally rather than vertically. So why have a PDF that's vertical rather than horizontal? So I started doing the newsletter in a horizontal format. But now, with the tablets, I'm not sure what to do. Anyways, we added a little color, and that was the last issue back in the spring. Now, IPSR, you can too. That's my saying for this talk. I know there's some authors here who have been in, who have appeared in PSR, and I encourage you to keep writing. You know, I'm always looking for articles. We don't have an extensive board to review the articles. If I could understand it, then, and I'm low tech, so if I could understand it, we go forward. Over the years, the 10 years I've done it, I don't think I rejected one article. You know, we're pretty open to anything digitally involved, and anything related to digital ham radio communications, and even non-ham. If it's something that would be pertinent to the hobby, we gladly accept it. And if you want a PSR, like I do, wa1lou@tapr.org, and I hope to see you filling my mailbox with articles. Format's no problem. I can deal with any kind of word processor program, and same thing with the artwork. I've been a tech editor and tech writer for over 40 years, so I got a lot of tools in on my Macintosh. Thank you very much.
All right, thanks, Stana. SDR versus legacy radios. If I can find his presentation here.
That's right. I don't have to bother with a hand mic.
Are you loud
Okay.
enough?
Let's try. Rhubarb, rhubarb, rhubarb. Does everybody hear me?
It's a little more gain.
Okay. Well, can you turn up, Scotty? Can you turn up the wick? You turn up the wick on the mic. It's a little light. 1, 2, 3. Rhubarb, rhubarb, rhubarb. A little more. Rhubarb, rhubarb, rhubarb. How's that? Okay. Well, first of all, Scotty, thank you very much for inviting me to speak today at the TAPR Forum. Oh, it's a little hot now. Okay. Okay, that should work. Okay, how's that? Okay. Okay, well, I'll to begin with stand and face the audience. As needed, I'll use the pointer. Again, I'd like to thank Scotty for inviting me to speak at the TAPR Forum today. This is a presentation which I originally gave at the Asia Pacific DX Convention in Osaka in 2016. It arose out of a discussion between myself and Mac JA3 USA, who is the organizer of the convention. He suggested I should give a talk on the relative merits of SDRs and conventional or legacy radios as seen from the perspective of the DXer or contest operator or the radio amateur in general. So I've put this together. But first of all, we'll start with a formal definition of an SDR. There's been quite a lot of discussion, especially with the advent of what I term standalone SDRs, namely SDR transceivers which do not require a computer for life support, basically a box with knobs, which is a direct sampling and digital upconversion SDR, such as the IC7300 and IC7610. The charge has been laid that these are not true SDRs. Well, that's all wrong, because they fully comply with this ITUR definition of an SDR. A radio transmitter and or receiver using a technology that allows RF operating parameters to be set or altered by software, including changes to operating parameters which occur during normal pre-installed and predetermined operation. In other words, if central functions of a typical transceiver, such as mixers, local oscillators, IF amplifier chains, and other signal processing circuits, are completely eclipsed by software, and where, with the exception of RF front-end filters in the receiver or cleanup filters or harmonic filters in the transmitter, all the operating features and parameters of the radio are determined by software. This is a software-defined radio as described in this ITUR recommendation. SDR and cognitive radio technology are rapidly displacing legacy radio architecture in critical military, government and commercial applications. Certainly all the RFPs that are coming out today specify either SDR or an extension of the concept which is cognitive radio. In other words, radios which embody a measure of artificial intelligence and are able to deduce their RF surroundings and their operating environment and configure themselves accordingly. Several new OEMs as well as a strong open source group are building SDR transceivers and receivers that rival and even surpass legacy radios. Established manufacturers are making the transition to SDR. with ICOM having been the one which has the highest profile right now. This presentation will explore the relative merits of SDR on legacy radios from the user perspective. We're only going to look at two SDR architectures, two radio architectures, the legacy superhet with a DSP backend and the direct sampling digital upconversion SDR. I'm not going to talk about the homodyne or Taylor mixer type of SDR because this was an intermediate step. As both topologies employ such familiar DSP-based features as noise reduction, noise blanking, notch filters, passband tuning, compression and so forth, I'm not going to cover these here. There are a lot of abbreviations in the SDR world. I won't dwell on them here, but if you want to study this material further, there's a link at the end to my website, which is alpha-bravo-4-oscar-juliet.com, and a PDF version of this presentation is linked from the test reports page, which in turn is linked from the home page. So my website is alpha-bravo-4-oscar-juliet.com. The most important abbreviations you're likely to run into when considering direct sampling SDR are the analog to digital converter ADC, DAC, digital to analog converter, FPGA, a field programmable gate array, which is a custom processor, a programmable custom processor made up of arrays of gates in a large chip, which can be configured by the programmer to carry out an enormous variety of tasks. Every modern FPGA, every modern SDR transceiver has at least one FPGA inside it. Numerically controlled oscillator replaces the traditional VFO or local oscillator. It's something like a DDS with digital output. Another concept that comes up, not only with SDRs, is passive IMD, or PIM, or PIM, which is IMD caused by nonlinearities in things like ferrite cores, some capacitor dielectrics, certain types of diodes, which can cause serious degradation of receiver or transmitter performance under strong signal conditions. Well, here's an outline of legacy versus SDR topology. The legacy superhet with an IF level DSP, examples of such radios that come to mind are the ICOM 756 Pro series, the Kenwood TS590, the later Yaesu radios, such as one that comes to mind almost immediately is the FT450, which was a small radio, but it was a superhet with a DSP backend. Basically, it's a superhet until the final IF is handed off not to a demodulator, but to an ADC, an analog to digital converter, typically at 30 or 36 kilohertz rather, which then passes the bit stream created by the ADC to a digital signal processor, DSP. Now this DSP does all the functions that you normally associate with the back end of a receiver. Selectivity, AGC, notch filter, and then some features that were not really convenient with a purely analog solution such as noise reduction. The noise blanker has moved from a very complex analog circuit into some DSP code, which generally speaking works a whole lot better. So the DSP chain in a legacy transceiver is a mini SDR operating at the final IF. Next we have the direct sampling and digital upconversion SDR. In the receiver, the ADC samples at RF. The output of the ADC is a digital bit stream which is digitally down-converted or decimated by a digital down converter or decimator with an NCO, numerically controlled oscillator, analogous to the mixer and local oscillator in a superhead. So it's kind of, you could call it a digital superhead almost, excepting it doesn't add noise or distortion. And it doesn't have frequency stability problems if the clock is stable, which it is. The clock is a high quality crystal oscillator, which clocks the ADC and all the signal management circuits or signal management functions in the downstream part of the receiver or the portion of the transmitter after the audio has been converted to a digital bit stream by an audio ADC. In the transmitter there's an audio ADC, there's a DSP function, and then digital up conversion, which is the mirror image of the digital down conversion in the receiver. And then the output of the digital up converter is fed to a DAC, digital to analog converter operating at RF. This generates the excitation signal which goes into the PA chain and develops the transmitter output. The numerically controlled oscillator is tuned to the operating frequency by a CPU inside the radio. And these functions are usually incorporated into the FPGA, which I mentioned earlier. Some designers are looking into the use of a commercial computer graphics processing unit, or GPU, to carry out the functions normally resident in the FPGA. And the reason for this is an FPGA is a one-way programming process. You write an image in software, and then you program it into the FPGA, and after that you better hope you're right, because you can't read back the FPGA. If it doesn't work, you've got to re-examine the image and redo the image if necessary. So to get away from this, some designers are looking at the possibility of using a commercial GPU for this function. And GPUs are inexpensive because they're used widely in high-performance general-purpose computers. Now, in all of these radios, in the receiver, the RF preselector, any preamps and attenuators, the audio chains, and the transmitter RF PA chain are common elements, both for the legacy architecture and for the DSP. There's very little difference between them. I've got a few block diagrams I can show you here. This is a typical, it's an ICOM radio. In this case, the IC7600. The RF signal comes in through a bandpass preselector and a preamp which isn't shown. And there are two thirst mixers because the radio has dual watch. It can receive two signals simultaneously on different frequencies within the same band and the same mode. The output of these mixers goes through a roofing filter, which is a cleanup filter. Purpose is to protect the second mixer from strong out-of-band signals. Goes into a second mixer, and then this was, I'm sorry, I'll backtrack. This is the 756 Pro series. This is the output of the second mixer goes through a 455 filter into another mixer stage, putting out a 36 kilohertz IF going into the DSP. In the transmitter, the process occurs in reverse. The audio goes into the DSP from which has a DAC, an audio ADC on it, or a codec, typically a 24-bit audio codec. The output of the DSP goes into a DAC, also on that board. It comes out as a 36 kilohertz IF, which is up converted and then transmitted. So in a direct sampling receiver, the ADC and FPGA replace all the blocks between the preselector, the low-pass filter or bandpass filter, and the DSP input. In a digital up-conversion transmitter, the FPGA and DAC replace all the blocks between the DSP output and the exciter, low-pass filter, or bandpass filter group. These are the cleanup filters in the exciter which deliver a signal free of harmonics and spurs to the PA chain. So again, the DSP is a mini SDR operating at 36 kilohertz. Now there's a newer type of legacy architecture which uses an IQ second mixer in the receiver. This has been used successfully by ICOM and Yaesu and Rockwell Collins. The output of the first mixer is fed via the roofing filters to a second mixer which has an in-phase and quadrature mixer. They develop upper and lower sidebands which are 180 degrees apart. The unwanted sideband is cancelled, and this mixer is able to down convert the 64 megahertz first IF directly to 36 kilohertz in one step, eliminating the 455 IF. The price that has to be paid for that is that the second mixer has to be designed to be carefully balanced and to retain its balance over the life of the radio, although it can be realigned if need be. Then the output of the 36 kilohertz IF output goes through into an analog to digital converter again, an ADC, into the DSP, which incorporates the AGC function, IF selectivity, IF gain, and AGC detection. There are two AGC loops. One is within the DSP, and the other is before the selectivity, which detects strong signals outside the receiver passband and uses these to control the gain of an IF amp before the second mixer, thereby adjusting the level of the final IF to be within the dynamic range of the analog to digital converter. So the radios such as the 7600, 7700, 7800, 7800, 7851, and also the Yaesu FT450 use this topology. Now, here's an example of a direct sampling receiver, the Flex 6500 or 6700. All signal processing takes place within the radio. The PC, in the case of the Flex radio, is just a control panel, user interface, display, and control. There are some other SDR designs, such as, for example, the OpenHP SDR, which is commercially manufactured by Apache Labs as the ANAN series, where major signal processing tasks are still conducted within the PC. The received signal is digitized in the ADC, which is a high-performance ADC clocking at 260 megahertz, and after having passed through pre-selectors and a preamp and attenuator, the analog signal from the antenna is fed to the ADC, goes into the FPGA, where it's processed as I described previously, and the FPGA feeds a bit stream to a very powerful combination DSP and CPU running at 1.4 gigahertz. And this puts out a 1 gigabit Ethernet bit stream to the computer, which is one of the options for audio recovery. Okay, one of the options for audio recovery and also for the control of the radio. On transmit, we just quickly look at the transmit part. There's a codec which converts the mic audio into a digital bit stream. Again, this is processed in the DSP and the FPGA. It goes into a DAC, is converted to drive excitation, which goes through the PA and the harmonic filters, and the ATU to the antenna switch. The ADC, DAC, FPGA, and other components in the radio are clocked from a precision clock source, which can in turn be clocked from an external reference. Now, the ICOM IC7300, which has by now become very well established in the amateur equipment market, is a standalone SDR. All its functionality is built into the radio. It doesn't require a computer. The 7300 has a slightly different approach. Again, the receiver has the ADC, the ADC. All these functions are digital. You can see the IQ mixer here, but it's done digitally, so it doesn't add noise or distortion. Its output, which would normally be a baseband centered around 0 frequency, is up-converted to 36 kilohertz to generate a pseudo-IF, which is passed into the DSP and processed just as it would be in a legacy radio. In the transmitter, again, the audio is digitized, passed through the DSP, through up-conversion function in the FPGA, which delivers a clean RF signal to the transmitter. The ICOM 7610 takes this a step further by having two completely independent receivers with pre-selectors, a tracking pre-selector, switched bandpass filters, a high-performance ADC, 16-bit rather than 14-bit, which gives additional dynamic range and better overall receive performance. And again, in the FPGA now, the DSP functions are contained within the FPGA, so the radio doesn't have a separate DSP. And there are two digital to analog converters here to get back to audio for the two receiver channels. And the transmitter is the mirror image of all of this. The sub or secondary receiver is electrically and physically identical to the main receiver. The architectural advantages of an SDR eliminates all the legacy subsystems with their impairments: mixers, analog local oscillators, roofing filters which have passive IMD phase distortion, insertion loss, IF leakage, etc. One filter called an anti-aliasing filter is required to suppress the aliasing response, which is the digital equivalent of an image response above a frequency which is half the sampling rate. So that's just one low-pass filter ahead of the ADC. Digitization of the payload signal at the earliest stage. Signal management is entirely digital. No noise or distortion are added. Software-defined signal processing greatly facilitates the addition of new modes, protocols, features, etc. Cost-effective customization, and a feature used in the ADC called dithering, which breaks up IMD products into a very slight increase in the noise floor, thereby reducing the impact of IMD on the receiver performance. Simplified maintenance, virtually no hardware alignment points anymore. Adjustment and calibration parameters are accessible via secured software menus, and interfaces to other equipment are easily configurable. Greatly reduced component count, cabinet size, weight reduced, reliability is increased, potential reduction in standby power consumption, and potential cost reduction. With the 7610 you have a radio which is very close in performance to the 7851 at about a quarter the price. SDR dynamic range considerations. The ADC clip level, the level at which the output of the ADC is all ones, sets an absolute limit to the signal level that can be applied to the input. The ADC is exposed to all the RF signals in the RF passband, limited only by the preselector, which is like a roofing filter several megahertz wide. So the ADC has to be, the level going into the ADC has to be managed to avoid overload of the ADC. The trick when running a direct sampling receiver is to adjust the attenuation ahead of the ADC or the RF gain control such that the noise, the band noise, is just above the receiver noise floor. In this way you can use all the dynamic range of the ADC. It's an absolute no-no to go and turning on preamps on the lower bands, were such as 40 meters, 40 or 80 meters, or 160 meters, with the band noise, excuse me, is 10 to 12 dB above the receiver's noise floor. The input power imposed by ADC clipping requires a different approach to AGC design. The AGC in a legacy receiver adjusts the audio output over a wide range of RF input levels. In a direct sampling SDR, the AGC is designed to keep input to the analog to digital converter below the clip level when strong signals are present in the receiver passband. Some SDRs have an indicator which tells you when the ADC is about to clip or clipping. The operator can also set the ADC input level via a manual RF gain control, which adjusts an attenuator ahead of the ADC, or by a step attenuator. There's one SDR designed by Rockwell Collins, which has dual AGC loops. One is derived from within the DSP and controls the gain of the first stage of the RF amplifier, in other words, what we commonly call the preamp. The second stage AGC is derived from an out-of-channel detector, which detects strong out-of-band signals, reduces the gain of the second RF stage without degrading the noise figure of the receiver. And this is used in a new airborne HF transceiver, which Rockwell Collins have just recently launched, I believe. Okay. We're running out, we're getting a little bit short of time here, but there is a discussion here of the noise floor of a noiseless 16-bit ADC compared to the real world. It's possible by a simple calculation to predict the performance of an ADC mathematically. If you calculate the dynamic range of an ADC from the data sheet, you'll get a number in the 70s. The noise floor is at 76, 77 dB below clipping. But okay, if you calculate the process gain, which is 10 times the log of the difference between, of the RF bandwidth divided by the detection, or if you like, the IF bandwidth, although there really isn't an IF, you get a large number in the 50 dB range, or even more if you're using CW rather than SSB, and you add the 50 or so dB to the 77 dB noise floor of the 77 dB native dynamic range of the ADC, and you get an acceptable dynamic range number. If all applied signals are equal in amplitude and phase, this theory will fall apart, but that, in practice, that seldom happens. There's a discussion here of dither. Dither is an on-chip function in which a pseudo noise generator operating in the digital domain has its output converted to an analog pseudo noise, which is added into the ADC input. At the output of the ADC, the digital version of this noise is inverted and stripped out of the bit stream, so the damage done to the signal in the ADC by the addition of noise is undone. But what this does is it breaks up or decorrelates unwanted signals such as IMD products and spurious tones, and dramatically improves the performance of the ADC. The spectrum scope in an SDR is driven directly from the ADC, and it can be as good as a lab spectrum analyzer, as you can see here. The problem that comes across again and again in SDRs is latency, the transmission of delay across the receiver or transmitter between the input and output. In a legacy radio, this is not a major problem. Typically, the latency is 15 to 20 milliseconds. Direct sampling SDRs exhibit latency ranging all the way from 5 milliseconds to more than 400 milliseconds. One popular model has latency in the 160 to 165 millisecond range. The 7300 has 3.7 to 16 milliseconds latency. Latency is now a big topic, a big talking point in SDR design. There are mitigation measures that can be taken through manipulation of filter parameters, DSP filter parameters in the downstream DSP processing of signals prior to demodulation. The OpenHP SDR group has made remarkable strides, reducing receive latency to less than 20 milliseconds. As you can see from this curve, the lowest curve shows you what can be achieved in the ANAN radios by properly configuring the filters. Without losing in too much in shape factor. 20 milliseconds is quite acceptable. Okay, I'll just quickly run through the transmitter advantages. The signal remains digital until it gets into the first stage of the PA. The ADC and DAC clocks are the main phase noise contributors. A design with low noise clocks will eliminate transmitted phase noise, and as a benefit, the receiver doesn't have a reciprocal mixing noise problem either. Reciprocal mixing noise dynamic range, RMDR, in direct sampling SDRs is usually well over 100 dB. Analog IF filters are gone. Transmit latency in CW mode can be mitigated by keying the carrier in the FPGA. Power amplifier linearization is possible with a direct up conversion transmitter, such as the pure signal in the open HPSDR radios. And virtually no alignment points, much lower parts count. Operationally, you have your spectrum scope. 2 independent front ends are available in many designs. Ethernet baseband interface to a PC really speeds up the dialogue between the PC and the radio. And direct sampling SDRs perform best with gain management based on a good understanding of the relationship between signal strength, band noise, and MDS. So which is better? The individual operator's specific needs will determine the answer to this question. SDR can offer clear advantages over legacy architecture, but some top-ranking legacy HF transceivers perform superbly in a brutal RF environment, both in amateur service and in demanding military, government, and commercial usage. There's also the choice, do you want a radio with knobs, or are you happy to run a radio from a PC? With the SDR, in the SDR world, you have that choice now. Radio amateurs who've been comfortable with legacy radios may find that a standalone SDR meets their needs whilst providing a refreshing uptick in performance and capability. And here are a few links. The link I would recommend to you, that's bragging for myself, is my link, because that will give you the presentation which will allow you to study the material and the other links as well. So with that, yeah, I'd like to thank you all, and I hope you enjoyed the presentation.
Next, John Ackerman, N8UR, is going to talk about recording wideband data using SDRs during the eclipse. And you also have a VHF, UHF signal generator, right?
We'll talk only a little bit about that.
Okay.
Because it's not finished yet.
Okay.
Okay. Good morning. I've been playing with SDRs for a long time, and we can do normal ham stuff with them. But it turns out we can also do some really interesting things using SDR that traditional hammers just can't touch. And this is not, let's see if I've got a switch I need to flip here. That makes it better. Okay, there we go. What we can do with a software-defined radio that we can't do with a traditional radio is suck in a whole lot of data at once. Gulp it, don't sip it. The HPSDR, which is the one that TAPR helped bring along and that I'm most familiar with, can receive up to 384 kilohertz of bandwidth in a single shot. We can record all that data to disk and use that for later processing. As an experiment, I decided to try to do that during the eclipse last August. And one of the theories was, or one of the reasons for doing it was, I didn't really know what to look for. We thought there might be signal enhancement, signal degradation. We thought there might be Doppler shift because of the ionosphere moving. And not knowing quite what to test for, I didn't want to set up to do a one-time measurement and then miss the opportunity and have to wait until the next eclipse. So decided to use this eclipse as a way to test out the idea of recording lots and lots of data. The tools that I used were one of the Hermes HPSDR boards, and the magic bit was the software. I used GNU Radio, which I think we've talked about in these forums for many years. It's an open source drag and drop radio. You can basically pull a block over that says radio, connect it to a filter, decimation, frequency change, whatever you want to do. And on your computer screen, you can put that together, hit the button, and it runs. It's very, very cool. Come on. This was the receiver that I used. There's a lot of stuff here. Oops, I did not want to do that. I'm sorry. There are a number of, come on. I don't know what's happened here. I can't even get to the next slide. It's a problem. There we go. Let's see if that. Somehow the mouse got. I'm just going to keep going in this mode to avoid losing any time. Oh, this really sucks, friends. I did. It's somehow the mouse got. Ah, there we go. It got put into full screen mode. Now we're back. Sorry about all that. So there's a lot of blocks on here, and I don't expect you to read what's in there. But the key thing is, this is one block that represents the Hermes radio. Tom McDermott, N5EG, wrote this driver. It's called Hermes NB. This can receive up to 7 384 kilohertz wide chunks of spectrum simultaneously. And I set this up to receive 4, and then these are just file sync blocks. Each one of these is writing data to a disk file. And so I recorded the 80, 40, 30, and 20 meter bands for 8 hours during the eclipse. That did use a little bit of data, but you know what? Disk drives are cheap. I used a $50 terabyte disk drive and filled it. We did some other stuff as well that took some of the space, but each band for 8 hours took about 91 gigabytes of raw data. And that's an awful lot, but it easily fits on today's drive, so there's no reason not to use that. So we gathered all this data, and essentially I've saved the spectrum to disk, and I can play that back as if I'm listening to it on the radio. I wrote a number of other GNU radio scripts to do that. So the very simplest example, this is a working GNU radio script. We just have this thing which is reading the file from the disk. This is controlling the sample rate, and this is an FFT display. From that, we can do interesting things like coming up here, this is 1 minute compressing 8 hours of 80 meters CW into a 1 minute span. You'll see about 39 seconds in is when the eclipse maximum hit. If you look at the spectrum, you'll see over in here where the prime CW area, not much going on now, but that will build. And more stuff happening, and it gets busier and busier. I know a minute is a long time for attention span. Yeah. That was some kind of spur. That was not a pilot. Now look how busy things are. Now when the tint comes up, that was the maximum time. I put a tint in the slide. Okay, that's the peak. And now watch those signals go away. So we saw a definite propagation enhancement during the eclipse on 80 meters. We looked at 40 and 20, not nearly as defined a... okay. Then again, the advantage of being able to go back later, one of the questions that we had was there a Doppler shift because the ionosphere is moving up and down, the reflections are getting longer and shorter? Well, when I recorded 30 meters, guess what? That includes 10.0 megs, so I was able to copy WWV at 10 megahertz. And I didn't go through the equipment setup here, but and I was operating portable from up at a cottage in Michigan, but I took a cesium frequency standard with me to provide the clock, so we know that I'm stable. Well, not mentally, but and we're looking at WWV, and here's this swing, and there's the eclipse maximum. Again, I recreated this after the fact. I didn't have to worry about trying to do this during the show. I also looked at WWV to see what happened with the amplitude. I'm not quite sure what to make of this, but it seems to me that around the eclipse time, the overall noise variation went down. The signal became more stable during that time. I don't know if that's just my eyes or a real effect, but it was something that we saw. And by the way, Nathaniel, who'll be speaking a little bit later, is doing all sorts of analysis on this kind of data to learn what really happened. I'm not the scientist, I'm just the observer. Now, I also recorded the AM broadcast band. I used a red pitaya to do that. The red pitaya can look like an HP SDR. It can also record a full up to 2 megahertz of bandwidth simultaneously. And that's what I did here to cover the whole broadcast band. I did a whole lot of post-processing afterwards to look for every single AM channel for 8 hours, look for what's the greatest difference in minimum and maximum signal strength during that time on the theory that there's a big difference that might have been affected by the eclipse. Then I took the 10 stations that showed the greatest change, and I plotted those. And you can see here, this is the eclipse maximum right here. Look at how these stations all came up. Notice also these are all on the top end of the band. Now, something very interesting, this guy is different. There was no carrier here that I observed, but just noise level. But look how that noise level went down during the eclipse period. That was down at 590 kilohertz. So a question is, was there, in addition to a signal enhancement, was there something that caused the noise level to drop? So lots more to explain and understand here. But again, I spent a few weeks going through this data multiple times in multiple passes to pull out this information. Doing it in real time never would have been possible. We can go back and do that. Now, this is all looking at analog, spectrum analyzer kind of stuff, which is something I'm familiar with because I'm an old RF guy. But we can also move into the digital world. Come on. This is the GNU radio script that was part of what I did. It's got a lot in it because we looked at 110 channels simultaneously. So we can move from analog to digital. The idea was take all this band data that we recorded to the hams and feed it into CW Skimmer and pick out all the CW calls, and we can plot their signal strength. In the interest of time, I won't go through all the interesting technology that we had to use to get from the disk file into the skimmer to log the data, but again, it was all thoroughly doable. Special thanks to N1GP, who didn't know he was doing it, but he wrote the magic software that let this work. We looked at 5 bands. There were no signals on 160 and really nothing on 30. I did a lot of analysis of 80, 40, and 20. For today, I'm only going to show you 80 because we have limited time, and that's the band where the most interesting stuff happened. So what I'm going to show you is the data that came out of the skimmer for stations heard on 80 meters during the 8 hours surrounding the eclipse. So we fed the data in and munged this all to ultimately make some pretty pictures that showed the activity level and also the average signal to noise ratio of the stations. So this is spots per minute. This is all 3 bands of 80, 40, and 20. This is 80. 40 and 20, it's a little bit hard to see a lot here, but look at on 80 meters how very little activity, and again, for about an hour around the eclipse, a lot of activity, and then a rapid drop-off. Now, it's possible that that's because people came on during that time period, and that's when they were operating. It's also possible that we heard a lot more because there was band enhancement, because the eclipse makes it look like it's nighttime for a little while. 80 meters comes alive at night, and that may have been what happened here. Now, this is the average signal to noise ratio, and again, we see fairly low numbers and then a big increase and then a rapid drop at 80 meters. Again, 40 and 20, it's a little bit hard to tell what really happened, but on 80, this is really apparent. And since this isn't based on amount of activity, it's sort of quality. how strong the signals were when I heard them, you know, we can say that this is probably related to the propagation effects from the eclipse. Just for fun, I took all the data, pulled out all the call signs that I had. Nathaniel built a database of all the SEQP participants and got lat-long information. He sent that back to me, and I then plotted with this neat tool that I found online. I was up here. I was on an island in the middle of Lake Michigan, about as far away from the eclipse as you could get in the continental United States. And these are the stations that we heard on 80. Again, it's not a perfect distribution, but we did have a little bit to the west and out to the east. This was the population that created the data that we looked at a minute ago. This is just another example looking at signal to noise versus history by itself. It's the same information that was on the first slide. This is looking at east versus west. As the eclipse moved, I thought we'd see enhancement first to the east, or to the west of me, then to the east. You can sort of see that here. The east peaks later. The west doesn't really peak that much, but again, if you go back and look at where the stations were, the stations to the west of me were actually south of me. There wasn't a lot of real west data, so that's not really a good data point. And if you do watch an eclipse, make sure you have your protection to make sure your eyes don't get hurt. That was our cat actually, my wife did that. It was so two other quick points of what you can do with this technology. Over in the TAPR booth, we have actual signals on the SDRs that we have running in the booth. Those signals were recorded during the eclipse and are being played back now using another GNU radio script. We have a little antenna underneath the desk, and we're playing back and listening on the radios to the actual CW signals that we recorded during the eclipse. So that's another neat thing that you can do, capture the entire band and play it back later. And one thing, I think they may be doing this already in contests, but if you have a contest that you're concerned about people cheating, might recording the band for later examination be an interesting way to police contest activity. So, and with that, I'm not going to talk about the VHF thing because it's not built. I got 8 minutes? Oh, okay, then I will talk about the VHF thing. No slides for this part, but I'm working on a project that's a little bit TAPR and it's a little bit VHF operator, and it's a little bit personal weather station. I'm sorry, personal space weather station, which Nathaniel will talk about. But there are lots and lots of synthesizer chips today that can create whatever frequency you want to drive a transverter or a local oscillator for another radio or a beacon. And a lot of them really have crappy performance. Some of the stuff that hams are using, the little Silicon Labs chips, the phase noise is really pretty bad on a lot of those chips. There are a couple of them that are really, really good. And we're working on a design now that will basically let you have one reference frequency, say 10 megahertz coming from a GPSDO or from an oscillator, and you can generate up to 4 independent outputs, anywhere from 100 kilohertz to a gigahertz, with 1 hertz resolution and very, very low phase noise. Right now the schematic is done, the evaluation board testing is done, we're working on the circuit layout. So hopefully by DCC we'll have something that will be getting close to available. But the idea is this board could be used as a better clock to go into your red Pitaya, which has a really lousy frequency stability because of the 15-cent crystal in it. We can use this to generate the clock frequency in the Pitaya or in any other SDR. Think about a stack of transverters if you're a VHFer. Get all the local oscillator frequencies for 4 transverters out of the box, or 4 beacons. Generate the frequencies for 4 VHF bands directly. So this is kind of a crossover product, and I'm hoping that we will have that available before the end of the year, and hoping that it will find use in a number of different applications. And with that, if we have another minute, I'll take questions or I'll shut up.
Questions?
I know I talked fast because I was afraid we were behind, so clarifications are possible.
It's a comment. The 80-meter drop-off you saw was the same thing we saw in Michigan.
I'm sorry, I couldn't hear you.
The 80-meter drop-off you saw was the same thing we saw in Michigan.
Yeah. Okay. Oh, I'm sorry. Yeah. Vic?
Yeah. You said you use GNU radio with Windows. Does that work very well?
I use GNU radio with Linux.
Okay.
It will run on Windows. I hear that it's working better and better on Windows, and they've now got an installer package that will, make it easy to install and run. But I've never had the courage to try.
Anyone else? All right, thank you, John.
Okay.
Stand in front of that.
Thank you.
W2, okay. And he's going to talk to us about HamSci. And how many people know what HamSci is? How many people don't know what HamSci is? Okay, good. Well, you're about to find out.
What kind of adapter do we have here?
It's
Oh, it's HDMI. Can I use your PowerPoint?
You can.
Great. Oh, that's yeah, I have it loaded on a thumb drive. We'll find out. It says sign in.
This is high-tech lab work. That's why he's got the lab coat. You don't want to see what you're doing.
Did you read that?
So while we're waiting for Nathan to get set up, don't forget the evaluation forms in the back. Please fill them out. Let Hamvention people know what you thought. Even if it's bad, like I said, if it's bad, you can put Steve Bible down as my name, but otherwise you can put my name down.
Okay.
Okay, Nathan, take
All
it
right.
away.
Thank you very much. Good morning, everyone. My name is Nathaniel Frizzell. I'm W2 NAF, and I'm a research professor at New Jersey Institute of Technology, and I am the main person behind starting HamSci, along with a few other people. So what is HamSci? HamSci is a ham radio science citizen investigation. And we're an organization, although that's kind of a loose term. We're more of a website and a listserv, but we have a number of main objectives. And that's to advance scientific research and understanding through ham radio. It's to encourage the development of new technologies to support this research. And that's where having HamSci work with TAPR is really good, because TAPR is very good at developing new ideas and really implementing them. And we also want to look to provide educational opportunities for the amateur radio community and the general public. And as I said, I really became what I am today because of ham radio. I started in like 8th grade and I just followed it straight through, and it led me to where I am now. So once I became a graduate student and I was working toward my PhD, I really saw this neat place where we could join the scientific research I was doing in school with the whole ham radio community. So we now have many different people who are part of HamSci. We have a Google group, which if you're interested in joining, you can come talk to me and I can add you to that. And we have members from just institutes and universities all over the world, including, and we also include just members of the general amateur radio community can participate. And so what I'm going to do in this presentation is I'm going to show you a number of slides from different projects that other people are working on, and also some of the things that I'm working on. So there's a little bit of a combination. It's kind of like a smorgasbord of activities. So one thing we have, this is from Bill Engelke, AB4EJ. He's at the University of Alabama, and you might know his website, the DX Display. And so what he's doing is he's aggregating reverse beacon network, WhisperNet, PSK reporter spots all into a single database, and I've started talking with him, and he's now incorporating space physics indices from the NASA Omni data set, so we can start combining this into what we call the HARC database, the HamSci Amateur Radio Communications database, so we can start doing data analytics and trying to understand all of this. So that's Bill Engelke's work. Joe Dzekiewicz, K1YOW, he has been working on looking at 6-meter spots, and he's been trying to understand the relationship between weather systems, especially like upper level lows and low pressure systems, and sporadic E, and he's finding good relationships there. He had some article, a really good article in the December 2017 QST, so you can read about that. And now he's been working on some new observations looking at how sporadic E forms on the jet stream and looking at correlations there. One of my friends up in Canada at the University of Calgary, his name is Gareth Perry, and he's not a ham yet. We're still working on him, but he's a researcher like myself, and he has access to this satellite known as Cassiope, and it has an HF receiver on it. So a couple years ago, we had him had the satellite listen to the HF bands during field day, and he's been doing some research with that. So we have a spectrogram, like a waterfall display that came off of the satellite, HF, and then this is a time series plot of that, and you can read K9 ESV field day right in there. And he actually started looking at some of the oscillations that ride on top of the CW that people were transmitting, and he was able to relate that to some physical processes in the ionosphere. And so this paper is currently under review in radio science right now. So hopefully this will come out. And it's really neat that we're starting to see peer-reviewed scientific publications come out of looking at the ham radio observations. John Ackerman talked a little bit about the personal space weather station. This is still just an idea right now. It's not like developed. But the idea is, in space weather, we use tools like magnetometers and radar systems and radio receivers to try and understand what's happening out in space. And so can we develop a single personal package that would let us, that you could set up in your backyard, that would sense many of these different things and help contribute to understanding global space weather through your individual measurements. Kind of like you can go buy a personal terrestrial weather station right now, tropospheric station, and you can plug that in and send your observations to Weather Underground. You get both an idea of what's happening at your location and also contribute to a bigger database. This is something that we're looking at developing right now. It's still just an idea, so if you have ideas to contribute to that, let us know. We had the eclipse. So John just talked all about his wideband observations of the eclipse. We have been also doing other sorts of observations for the eclipse. This is from Magda Moses, KM4EGE. She's a student, also one of the people who helped start HamSci. This is observations from the SuperDARN radar in Oregon, and a SuperDARN radar is a high-frequency radar. So it transmits between 8 and 20 megahertz, generally outside of the ham bands. And it will look for ionospheric irregularities and also look for ground scatter, and you can get ionospheric measurements from that. And so with these observations, she's starting to look at how the eclipse affected the HF spectrum using these research radar systems, and you can see a change in range of the radar scatter here during the eclipse, and she's starting to use ray tracing programs to help model that. And of course, I coordinated the Solar Eclipse QSO party. How many people here participated in the SEQP? That's great. Did you have fun? Yeah? Okay, so I really wanted to do this because I've been looking at the reverse beacon network data for a while, and I've seen a few other QSO parties, but I really wanted to see if we could make a scientific experiment that really felt kind of like a ham radio contest, because a lot of people, I always enjoy contesting and many other people do too, and so that's what we did. And so this is a map of the reverse beacon network observations. All of the color-coded points are halfway points between a transmitter, like you out in the field, and a reverse beacon network receiver, which is a star. So all the black dots are transmitters, and there's 1,184 transmitters on this map, and 49 RBN receivers, and over 312,000 RBN midpoints there. So it's a tremendously large data set around the 8-hour period of the solar eclipse QSO party. And so I plotted this out like that, and then I organized the data so that we could see how the bands change relative to time before and after the eclipse. And you know, it's a lot of what you'd expect. It's very consistent with previous experiments, but here's 20 meters on top. This is an hour and a half before the eclipse. This is an hour and a half after the eclipse. And then right down the middle is where eclipse maximum was at any particular location. And you can see 20 meters was going gangbusters an hour and a half to a half hour before the eclipse. And then things just died off. And then it came back about a half hour after the maximum eclipse ended. 40 meters, you expect things to start going long in the evenings as you get into gray line propagation. That's what we saw here too. So we had good propagation before the eclipse, an hour and a half before. As the eclipse comes on, you see the typical distance of QSOs go from about 500 kilometers to about 1,000 kilometers. And then when the eclipse goes away, then we get the communications come back into about a 500 kilometer typical range for your 40 meter communications. For both 80 and 160 meters, we saw band openings. 80 meters was opened first. It opened up about a half hour before to about a half hour after eclipse maximum. And 160 meters, that opened up about 15 minutes before and ended about 15 minutes after. So we really get, from this large data set, we're able to condense those observations down and see some really nice things. And so I'm very happy to say that just this past week, these SEQP observations I just showed you were accepted into geophysical research letters. It's a peer-reviewed journal, well known in the ionospheric community. And so this is published open access, so you can go to hamsci.org, you can get the link, and you can download and read this paper and see all those figures yourself. So this is really exciting. I think this is really a nice showing of where we're actually taking the amateur radio observations and really starting to publish and push science forward. So please come visit our HamSci booth over in the Volta building, and we look forward to hearing your input. If you're interested in being involved, I'll add you to the listserv. And it's really, HamSci is very much a discussion, so you can be part of that discussion. So thank you very much.
Oh, when is your forum?
What's that?
Your forum.
Oh, and we have a forum tomorrow morning, 9:15 a.m. in building Forum Room 4, which is like far away.
Behind the bleachers.
Behind the bleachers, yes. So if you want a nice walk tomorrow morning. The forum's going to be quite exciting. I'll be presenting the SEQP results again, but we also have Phil Erickson. He's the Associate Director of the MIT Haystack Observatory, which is a very large incoherent scatter radar run by MIT up in Massachusetts, and he will be talking. And we also have Angel Vasquez, WP3R. He's the Chief RF engineer and spectrum manager of the Arecibo telescope down in Puerto Rico, and he will also be there. So it's going to be a really good forum tomorrow morning. I hope to see you there.
All right, thank you, Nathan.
Thank you.
Nathaniel.
Thank you very much, Scotty. I appreciate it.
And we'll look forward to seeing you at your forum. And come by the building 4, right? Building 4,
yes, Volta.
And there's booth forums all day, short ones every hour.
Yes, it's
all different topics.
We're doing it in conjunction with Ham Radio 2.0. So the YASME Foundation has sponsored our HamSci booth this year, and they have also set up this area called Ham Radio 2.0, where we're trying to push the ideas of what ham radio is going to be in the future. And so TAPR and its ideas very much fit into that. I was actually really lobbying hard to get the HamSci booth closer to the TAPR booth, but we'll try to make that work for the future. So yes, the new building. Thank you very much.